All right, so this is our third lecture in Chapter 3, which is one-dimensional steady-state conduction. And this time we moved into this section on extended surfaces. Basically, it's an analysis of fins. How to promote heat transfer by attaching to a base additional material, a fin. And so often we have a surface and we want to, it's hot maybe, you have the temperature of the base, and you want to promote heat transfer into a fluid, T infinity. Often I think about the fluid being a little cooler, but it could be hotter, and you could have the other direction of heat transfer. But anyway, and you have the convection coefficient H with that. Well, what you could do is you could attach what they call an extended surface or a fin. This fin could be, I'm just showing you 2D. If I looked at it this way, it could be a round or a pin fin. Or it could be a rectangular fin like that. So there's different shapes. We're going to start by analyzing one that's of constant area or cross-sectional area. So as I move out from X, going from 0 at the base out to the tip L, that the area for the conduction through that cross-section, A sub C, is a constant. And so for a round pin fin that is a diameter d, A sub c is pi d squared over 4. And here for the rectangular fin, we talk about the thickness t and the depth w or width w. And in that case, the cross-sectional area is going to be w times t. What's that cross-sectional area? It's not changing, and it's conducting out that cross-sectional area. Okay, but as it conducts out, there's some heat transfer off of that surface into the fluid. That's the reason of having this extended surface, this fin, to have more area, to promote the heat transfer. And so we're going to develop some simple equations where we have the amount of heat transferred into the fin, which gets into the fluid. A simple equation would be the convection coefficient, that area of that fin, not the cross-sectional area. I didn't put a C on that. That's for the conduction, moving out further and further into the fin, times some T base minus T infinity. Think about the hot base and the cooler fluid. And then you're going to say, well, that looks like the whole the whole surface of the fin is at the temperature of the base, right? Well, we make a modification, we put there, right there. That is a Greek letter. Oh, I forgot the name of that Greek letter. Theta? Eta, that's right. And we put eta subscript F. That's going to be the efficiency of that fin. If the fin is made of super high conducting material, basically the base and the tip and everywhere along that fin have the same temperature, the base temperature, and eta would be 100%. But real fins maybe have efficiency of 90% or 80% or something, okay? And so what we're going to find is, after a lot of math, we're going to set up a governing differential equation to predict the temperature profile through the fin. Can anybody guess what the governing differential equation would look like? Well, we've been playing with the similar equations all chapter. And so it's going to be one-dimensional, so I just have a second derivative of temperature with respect to space. I'm going to have a K and an A sub C for moving conduction down. Then I'm going to have an H and a P. P is a perimeter. If I go back to my pin fin and I say, hey, what's the perimeter for my pin fin? It's just pi d. That's that length. For a given location X, what is the length of the perimeter? How about for this rectangular? The perimeter would be 2w plus 2t, and a lot of times we neglect the length. 2t is small compared to 2w, and a lot of times the perimeter is just 2w. Okay, but that's what we mean by p, the perimeter. And then we're going to have t minus t infinity. Or they rewrite this equation, the second space derivative of theta is equal to m squared theta. And you say, well, what is theta? Well, you can guess what theta is. What's theta? T minus T infinity. Temperature difference. What's the temperature difference between the location at that point X in the fin compared to the fluid temperature? Well, you tell me. You're budding mathematicians. You've taken all these hours of calculus and engineering analysis. I have a second order differential equation. I'm going to need two boundary conditions, and then I'm going to need a strategy to solve for it. So theta at x equal to 0 is the theta at the base. And then typically we use insulated tip boundary condition, d theta dx at x equal to L is equal to 0. Insulated tip. How are you going to solve that well-posed mathematical problem? Yeah, you know, if you listen to me, you'd probably try to recite, oh yeah, he's asking a question about what I learned in Engineering Analysis 1, separate and integrate. And that will do well for 90% of that class. Or maybe not 90, but a high percent. But guess what? Won't work here. It's called guess. Yeah, method of undetermined coefficients. It's called guess the solution. So you guess sines and cosines won't work for this one. If there was a negative in front of that m squared, oh, it'd work perfect. And we'd have that oscillating omega t or whatever. But this one has a positive m squared theta. So guess what? It's not sines and cosines. It is, guess, exponentials. Your favorites, your exponential functions. So that's the strategy for this differential equation. Not separate and integrate. Fancy name, Zach, what'd you call it?
Oh, method of undetermined coefficients.
Method of undetermined coefficients. Mine is just, it means you take a form, you guess, you have some coefficients in there, you see if it works. All right. Well, we're going to then come out with an equation for this fin efficiency. And it's going to be the TAN. Hey, tangent, my old friend. Nope, add an H. What? What is TANH? Hyperbolic tangent. That's maybe not my close personal friend. I know the tangent was. It's a little distant. You know, I haven't seen this cousin for a while. And it's going to be the hyperbolic tangent of M. What is M again? A fin parameter, a fin coefficient. In this equation up here, you just work out the math. M is equal to the square root of HP divided by KAC. It's a fin parameter. I need to know the coefficient. I need to be able to get the perimeter. I need to know the conductivity of the fin material. I need to get the cross-sectional area for conduction going out. So then you multiply by L, that's the length, and you divide by ML. This is a simple equation, and you will see it throughout, let's say, thermal design classes where they have the student work out a design for a finned heat exchanger. You'll see it all over, okay? So when I teach something like thermal systems design, yoo-hoo, do you remember from heat transfer? Most of them need a little review. But yes, this is where we pull it out of this class. All right. Now, not is the surface, once we have analyzed one fin, then we look at real heat exchangers. Is there usually a heat exchanger with only one fin in it, or are there plenty of fins? There's plenty of fins. And so they'll have another fin right here, and another fin right here, and another fin right there. They'll have an array of fins. And then they say, well, what we'd like to do is we would like to work out an equation where we have the heat transfer from the array of fins is equal to some overall efficiency of my finned array times some convection coefficient times some overall total area times some temperature at the base minus temperature in the fluid. This really boils down to some simple equations. Why do I spend so much time on the intro? I suspect I will be able to put a few of you to sleep today, because of the highly mathematical nature of this section. And I want you to not get lost, right? We're going to go into some thick forest, for mathematical forest here for today. That's it. All right. So let's jump into it. Oh, the equation for the overall efficiency will be related to the single fin efficiency, and it'll have some area ratios. Let's get to that when we get to it. Okay, here's a picture of an automobile radiator, and so it's hooked up to the engine. Maybe the water flow comes this way and goes that way, and it's used to cool it. And there's maybe a thermostat that opens and closes to control the flow of the coolant through that loop in the radiator. So maybe here's the radiator. This one, they'll have the manifold to distribute it at the top, and they collect it on the bottom. Other ones will have it on the side, the manifold, and then but it'll flow through passages. Here they flow through passages that are straight down. So you can see they're showing hot liquid flow, and it's dropping, changing temperature. It's not so red hot as it flows through the radiator. And the bottom, it's a little cooler, and then it's collected out and it goes out the bottom manifold. And so the fluid flows down in passages in this radiator. Other radiators, side to side. Just take a look at what you have in your car. Top to bottom or side to side, either one. I think the majority probably are side to side. Anyway, so what do they say right here? Fins. What are they finning? Not what the liquid water with the little glycol antifreeze sees. That's usually a pretty smooth little passageway through the radiator. It's what the air sees that's coming over on this side of that radiator. And so we zoom in maybe a little bit, and when we zoom in we see, oh, this is my fluid liquid flow passage, and in between they put this material. Guess what that is? It's a fin. You can analyze that as a fin. Oh, we're going to make it look really, really pretty. We're going to have a straight line, and we're going to have out perfect little rectangles instead of this, and then, you take a little finger and you rake it down on the radiator. Don't do it. What will you do to those little fins? Crush them, right? And then it'll stop the airflow through that little section. Do you know what I'm talking about? Yeah, you shouldn't write your name on the radiators, or you shouldn't write your name on the condensing coil at the house, the outside condensing coil. Shouldn't do that. Actually, they sell to service technicians fin straightener combs. Like your hair comb, straighten your hair, they sell them. Anybody use one ever? Some of them, yeah, okay, straighten them out. All right, so those are fins. Hopefully you see the practical application of fins in your everyday life. What we're going to do is you say, what is the purpose of adding that little fin in our radiator? It's to make a larger rate of heat transfer. In this basic equation, we would like to have a large Q. Mathematically, that's how we interpret it. And you say, well, Q is a product of three things: H, A, and delta T. This is the type of thing I hope you don't leave this class with. But I'll be honest, when I took heat transfer, I definitely left this class not knowing this type of basic stuff. Oh, I could talk about all kinds of mathematical gyrations to solve problems on exams, but I had lacked some practical knowledge of how the class applied. So this is very simple. But if you wanted a larger Q, if you wanted to increase the convection heat transfer, you could, true or false, increase the convection coefficient H. Would that help? Do you think I should have that as a clicker question? Do you think that's too easy? It's a true, isn't it? You could increase the area that there is between the solid surface and the convection. That's true. And you could increase the delta T. That's true. Now think about my automobile radiator problem. I probably, when it's operating, I probably am stuck with, this is the temperature that my engine wants to run at. Anybody know what's the typical thermostat temperature of the automobile that they drive? Have you had to replace one? You can get the OEM temperature, you could get the high temperature or the low temperature one. Always go OEM, what the manufacturer recommends. Around 200, about 180, 195. They used to run them a little higher, like 210, 220, 230 in stock. Okay, degrees F, all of these. And then I would not recommend it, but they do sell some low thermostat, like 165, 160, somewhere in there. Mine never seemed to run well, either on the high or low. Just get the stock, what the original. So you're kind of stuck with this one, right? You don't want it too hot. And this one, how do they promote this one? Well, they put a fan to draw the air across the coil. The fan's not needed when you're going 60. Well, you're probably passing me on the highway. You're probably doing 70 on the highway. Okay, 70 mile an hour, you don't need the fan on. It's blowing, come on, right? But when you run up to a red light and stop, you need the fan, and you need a piece of plastic that goes around that fan and seals it with the radiator. It's called a fan shroud. I did this when I was about 17. Rebuilt an engine, took the fan shroud, just a piece of plastic, threw it out, don't need it. What happened? Anybody, similar story? Anybody do this? A couple people in 830 did. Yeah, nobody? You're smarter than me when I was 17 or 18. I ran up to the first red light, sat there, and watched my temperature climb. So, basically the fan shroud and the fan all promote H. That's what they do. They pull that air across that radiator, and that's what you want. Some of you have electronic fans, right, with the nice fan shroud. Is it always on, or only when the temperature gets up and then it needs to reject heat? You'll hear that fan kick in and off, but a lot of times it'll be off. All right, anyway, here it is. That's how you handle, that's what the purpose of the fin is doing, increasing A. You're kind of stuck, you've got a fan, you've got a shroud, get it finned. So, how does the fin work? It does not promote H. It does not promote a larger delta T. It increases the area. So simple. It's so simple, isn't it? Let's go. Why is it hard to dump heat into air and not as hard to dump heat into water? Why don't they fin the water side of my radiator? They only fin the air side. There's no fins that the water passage sees. It's just what the air sees. Well, the reason is you can't move air fast as water? No, come on. How about mass or density difference, specific heat difference? It's really in that thermal conductivity. Take a look, thermal conductivity of air. Remember, one of the themes I want you to leave this class with, it's a great insulator. Hold air stationary, you've got a great insulation. Well, if you're trying to dump heat into something that has a low thermal conductivity, that's a challenge. So that's why it's harder to dump it into air than into water. The water has a much higher, 20 times higher thermal conductivity. You say, 20, that's not a big difference. Okay, tell you what. You tell me your dream salary after you graduate. Okay, 100K. All right, great. I'm going to tell you, nope, we're going to take and do 20 times your dream salary. You going to be, you ready to go to work now? Huh? Yeah, 20 times is huge, huge. Sometimes you just look, oh, that's not that big of a number. No, it's huge. All right. Let's now go back to our discussion of fins, our round fin as well as our rectangular fin. First, we're going to analyze those that are constant cross-sectional area. This A sub C does not change as I move from the base to the tip of the fin. And we have the perimeter is defined for both the round as well as the rectangular. Often, again, for that rectangular, they neglect the little 2T, and this is just 2W. All right, somebody says, why are we going to be able to do a one-dimensional analysis of heat transfer? Isn't it 2D? Doesn't the heat have to flow both out in the X and then up in the Y to get to the surface and then off of the surface? Why don't we have both a 2D analysis? Well, you can justify it by thinking of it moving at a particular X. Maybe I blow this up right in here. Maybe this is my rectangular fin and this is my center of it. At a particular X, it's you're thinking about how hard is it to move from the center of that rectangular fin to the edge of the surface, and compare that to move it into the fluid. And think about this resistance, this conduction resistance internal to the fin compared to the convection resistance. Not the conduction from the base to the tip, but just from the center to the edge, that conduction, and then from the edge out into the fluid. Well, I know this is a long subscript. Resistance conduction from the center to the surface. What does that look like? Isn't it just a L over Ka? Sure. And you want that to be much, much smaller than the resistance convection to the surface. From the surface out into the fluid. Well, that's just a 1 over HA. So mathematically we write that like this. And then the A's can cancel, and you're left with H times some characteristic length divided by K, much, much less than 1. That effective or characteristic length for a rectangular fin is just that half thickness from the center out. That thickness was T. How about for a round? Well, okay, how about half of the radius, because it's, it's not moving from the center. There was nothing there for the area at the center. So the consensus is a good effective length is R over 2. You can check to see if this is true. The vast majority of the times, your H is low because of its air, and your thermal conductivity is good. You're going to pick copper or brass or aluminum with high K as a good radiator material, and so this is going to be justified. We're going to revisit this type of justification when we get into transient analysis and lumped capacitance. All right. Somebody says, I don't understand what is much, much less than 1. Well, start to develop your engineering judgment. All right? Is 90% much, much less than 100%? Is 0.9 much, much less than 1? No. How about 0.00000001? Is that much less than 1? Yes, that's definitely. That's easy. But here, the breaking point typically is about 1/10. Okay? This is heat transfer. A lot of times we don't know our coefficients, our H's or our K's that well. It's usually the H that's unknown with a higher degree of uncertainty. So if it's 1/10 or less, that's considered much, much less than 1. Now let's get to that mathematical equation, and then we can get to our hyperbolic stuff, our hyperbolic cosine and hyperbolic tangent, right? So, well, you have to set up from an energy balance and establish a governing differential equation. Start with a little control volume, shown here in purple. You have conduction, and convection. So there's the 1 in and 2 outs. How do you model the 2 conduction in and out? You use Fourier's law. The convection off the surface. That's how you have that cross-sectional area for conduction and that perimeter for convection. You then divide both sides by delta x. You do the little calculus trick. You say, oh, the limit as delta x goes to 0 of this ratio. And when I first started teaching, I would ask students a question at this point in the lecture. I'd say, okay, look at that. If I have f at x plus delta x, and I subtract f at x, and I divide by delta x, and I take the limit as delta x goes to 0, see that? I'm going to be dividing by something going closer and closer to 0. 1 over 0 is infinity. This blows up. It's garbage math. Worthless. And about half the class would agree with me. Yep, that don't work. It's infinity. But people are smarter now. This is 2017. You remember that from a previous math class. The limit, even though the denominators go into 0, what does that give you? The derivative. This is a fundamental definition of derivative. I know that's a few semesters back. You probably forgot it. But there you go. So you pick up that second derivative. And then this parameter m squared is this hp over ka sub c. A lot of times the book likes to write it in terms of a delta temperature difference, a theta temperature difference. And so here's our differential equation. I talked about how to solve it. You just guess the form. Sines and cosines won't work because you need the exponentials. And when you put it together, and there's a few steps in here with these boundary conditions, boom, 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 you get Cauchy's for your analytic temperature profile. So it's Cauchy, blah, blah, blah. So now you say, it's been so long, I need a review. Well, here's your quick review. This is the definition of the cinch. Does it look familiar? No? You're honest? You're honest. The Cauchy, well, if the cinch didn't look familiar, the Cauchy looks even less familiar, and the hyperbolic tangent is definitely less familiar. But the Cauchy is the cinch over the Cauchy. Oh, I'm sorry, the tangent, hyperbolic tangent, cinch over the Cauchy is defined like that. The one thing that we really need is our temperature profile used the Cauchy in it. So we're going to need to take the derivative of the Cauchy. And the derivative of the Cauchy is the cinch. Yep, without a minus sign or anything, just the cinch. And then we're going to use the tangent. That'll naturally come out of the math. So I think I'm doing a pretty good job putting a few of you to sleep. I saw some yawning. I saw some heads laying down. But let's press forward. Somebody says, I want the equation for the amount of heat transferred into that fin. Well, use Fourier's law at the base of the fin. You have now the temperature profile. You can get the gradient or the derivative of the temperature profile and evaluate that at the base. That will be what gets into the fin. What gets into the fin eventually gets out of the fin. So that's our equation. So here's our solution for the temperature we just derived. It had that Cauchy in it. I need to take the derivative of it, so I'll have to take the derivative of that Cauchy. It's one of these things where there's plenty of places to make errors, but other people have gone before you. And so what you find is that you can develop the equation where it's a few steps right here, where you have the hyperbolic tangent come in, the cinch over Cauchy. I had to evaluate this at x equal to 0. And so we rearrange some terms, and what we get is Q sub f is equal to this ratio, hyperbolic tangent ml divided by ml. Help me a little bit. What was L? What was L? The length of from the base to the tip, the length of my... What was M? The name of it. It's just the fin parameter. Square root of KAC divided by... Square root of HP divided by KAC. Just the fin parameter. All right. Then we have H. Then we have this perimeter times length. Hey, that's my area of the fin. And then this temperature difference. So it makes it look very similar. So this is now name calling, and we're going to call that on the next slide the efficiency. If all of the surface of the fin was at TB, the highest temperature, the base temperature, 100%, that would be the amount of heat transfer if efficiency is 100%. But our actual fin efficiency will be less. Somebody says we can use this in our guidance of how long a fin should be, because you can make a short, stubby fin that's not only physically short and stubby, but thermally short and stubby. Or you can make a physically long, slender fin, not only physically long and slender, but thermally long and slender. And here will come the criteria for what is the length that you definitely don't want to go beyond. And you don't want to go beyond because this hyperbolic tangent ML over ML kind of maxes out. That hyperbolic tangent maxes out to 1. And so if you come out here to about 2.65, it's 99% of 1, 0.99, close enough to 1. We would call that approximately 1 at an ML of 2.65. So don't take a physical length longer than 2.65 divided by the fin parameter M. Definitely don't. Most of them are well below that. Let's continue on. So we had this fin efficiency. So it's the ratio of what actually is transferred to the maximum if everything was at the base temperature, and we find that definition just falls right out. That's why we like this solution for insulated tip fin temperature profile. All right. A lot of times people will see this L sub C crop up and it'll replace L. And they'll say, what is this L sub C? It's a corrected or adjusted length. Conceptually, we liked a very simple formula, but this simple formula was based on an insulated tip solution. Somebody says, I may have convection off my tip. Okay. Well, if you have convection off the tip, as a budding little good engineer, you might want to think about that problem may be mathematically harder. What I'll do is I'll conceptually cut it. I'll flip this up a little bit, make it a little longer, flip this down, and then put insulated. So instead of using my actual physical length, I'll use a little longer length, where for my rectangular fin, the added length is the half thickness cut in half. The thickness cut in half. T over 2. Hopefully that makes sense to you. Think about cutting it and then flipping it up and then have it truly insulated. So you're allowing a little extra convection off of this little extra length. What about for the pin? Other people have thought about it. They say take the diameter, cut it in 4, make that a little longer. So all of a sudden, in the equations, it turns from L to L sub C. If you really do have an insulated tip, you don't need the corrected length. But if you have a convective tip, you do need it. Well, this is one of those sections of the textbook where I would say to the authors, move some of this material to the appendix. You're going to overload the students. The students are probably out there trying to read the book late at night and they're falling asleep. Right? You ever done that? Well, so this is what I would say. Don't pay too much attention to this case A or C or D. Focus on this one because that's the one we just worked out, the adiabatic tip boundary condition. We worked out that, I know they express it kind of funny, but this is theta divided by theta at the base. It's a dimensionless temperature ratio, temperature difference ratio. So there's your cosine. Hyperbolic cosine. And then this is that hyperbolic tangent that's used in our fin efficiency. Definition of M, and they even have a big M. I'm not in favor of having too many new definitions of terms, but there you go. If you want, you can actually do it for the convective heat transfer. You know, I just don't see a lot of that used out there in the literature. Oh, you can work it all out. You just have more hyperbolics, this, that. Okay, it's more complex. Mathematically, if you coded it up, it wouldn't be that difficult. But prescribed temperature at the tip, mathematically, you can prescribe it. It just is how often is that in practice? As well as, hey, let's have an infinitely long fin. What are you going to focus on when you study? The adiabatic tip makes for simple compact equations, which can be applied when you have a convective tip by using the L sub C, the corrected length. All right. The other thing is I would encourage them, it looks like the fin effectiveness and the fin efficiency are kind of given equal weight in the discussion in the textbook. To me, this is the big deal, the fin efficiency. The fin effectiveness, FYI, and there's so much stuff to keep straight in your mind. Try not to even put it in your mind. How's that? The definition is easy. It's just focus on the big deal, what's more important, and that's the fin efficiency. Well, what happens if you don't have a constant cross-sectional area fin? Let's say my fin has this rotational type of fin. As I move further out in the radius, doesn't the area go up and up and up because of larger radius? Sure. Well, there's not a compact solution that I know of, unless maybe it uses Bessel functions or other type of functions which you're less familiar with than the hyperbolic functions. So typically they plot these. So you're looking for, hey, I forgot, what is A to F? What's the name of A to F? Fin efficiency. Yeah, this is the most important parameter, the fin efficiency as a function of some other parameters for that configuration. They also have other equations. This one we worked out. This one they work out. And yes, those are Bessel functions, probably tabulated in the back of the book. All right. Since the advent of computers, the necessity to master Bessel functions has diminished. Aren't you glad? So once you have the single fin, you must be able to put it together into an array. You have multiple. This is not that hard, but think about it for a minute. What I want is I would like a very simple equation where I have not a single fin efficiency, but the overall efficiency for the finned array. So the heat can go at the base. This is all the base temperature here. The heat can go into the fin and then get into the fluid. We just analyze that to death. Or, you know what? There's spacing between fins. And it can come off of that exposed base that has no fin attached to it. And so there's two paths. You would say, well, it can go right from the base into the fluid or into the fin and then into the fluid. That's how you get the sum to be total Q. Well, then you just work it out. This is my model that I want for the total Q. This is the easy one. It's just HA, the base area that's exposed, times delta T. And then we just worked hard to get this one where everything is into this fin efficiency. All right. You cancel terms, you rearrange, and you come up with this. And it's really easy to read. You think about it. Okay, the overall efficiency is going to start at 100%, and then I'm going to subtract some. It's not going to be over 100. It's going to be less than 100. How much less than 100? Well, this is finishing out the equation. You have the area ratio, A sub F divided by AT. Even if I didn't show you before, what are all these? What do you think A subscript F is? Area of the fin. And then what about A subscript T? Total. The area of the fin plus the area of the base. It's the total area that you convect into the fluid. All right. And then we already know what this is. So this equation just naturally works itself out, and I think it's easy to read. All right, we're almost done. We just need to solve this problem. Zach, how much time do we have?
18 minutes, so we can start the quiz.
We can do that. 18 minutes, we'll start the quiz? Yeah, we can do this problem then. So here's a compact heat exchanger that has air passages. The air passages are 2 millimeters by 8 millimeters. So they're rectangular passages. This height is 2 millimeters, and this length of the air passage is 8 millimeters. That's the air flows, into each of these passages and down, and then there's the width or the length that the air passage goes, 10 centimeters. Okay. Between parallel plates. So this is a plate right here which connects this side with this side, and it forms the top and the bottom of our air passages. Okay. The plates have a depth of 10 centimeters, and we'll use the symbol W for the depth in the direction of airflow. Passages are created by walls that are 1 centimeter thick. So this is 1 centimeter thick on our walls, okay? And they act as fins, meaning they can conduct down the wall and then into the fluid. The wall conductivity is 200. If somebody said, I want you to guess that material, would you guess Let's do one clicker question today. A, B, or C. No looking at your notes. Just what would you guess this material to be? Would you guess it to be copper, aluminum, or some sort of iron? All right, let's go ahead and stop. Now, before we grade that, well, I'm going to ask another question. A, B, and C, what has the highest K? What is the best conductor? And actually, it has the highest price of these three metals as well, like per pound. So, copper, aluminum, or iron, what is the highest thermal conductivity? And I'm giving you a hint, it also has the highest price per pound or per ounce or whatever, measure of weight, measure of mass. All right, everybody in? Let's go ahead and stop. This one I'll grade. Let's go ahead and grade that. And you are absolutely correct. Copper costs more. They recycle it for a higher value, and also it has a higher thermal conductivity. All right? All right, let's flip it around and ask one more question. Let's say, of these three, what has the lowest thermal conductivity? And also I'm going to tell you, has the lowest cost. That's my hint. So, of these three, what has the lowest thermal conductivity? I'm curious, does anybody recycle in this class and actually take it down and sell? Like you sell? So, yeah, have you done aluminum cans? Do you do aluminum cans? Aluminum shavings from a lathe? What do you do?
We were just taking over about parts of the aluminum.
Well, aluminum definitely is more valuable. Aluminum's in the middle. And actually, you can make a little bit of money recycling aluminum, either the cans or that. This one, you just basically are saving the dump fee for the iron. I found that you take a whole truckload and you get a couple dollars. You could take a pail of aluminum and get more than that. And if you had any copper or brass, you could be a rich person. Forget it, you're never going to make a lot of money recycling. All right, so let's go back to this one at a value of 200. Which one do you think it was? Let's go ahead and just grade it. It's aluminum, around 200. About 400 for copper, and then around 50 to 80, somewhere in there for thermal conductivity to iron. All right, okay, well, at least I had two easy questions. The first question was hard, right? Sorry about that. Okay, let's move on. So electronic components dissipate heat uniformly on both side plates. So there's some side plate that there's a lot of heat, and what we're going to do is we're going to assume that the temperature on this side is all TB, the base temperature, and the temperature on this side is all TB. Both sides have some heat source, electronic components. They tell us that it's 45 C on those four sides, 45 degrees C. Airflow's in the passage. And airflow, you could say, comes in at 30 and really doesn't heat up that much and stays 30. Or maybe comes in at 29, leaves 31, average 30 degrees C for the air. And the convection coefficient is quite high, 125 watts per meter squared degree C. Calculate the rate of heat transfer to the air in one passage, in a single passage. Well, I have one passage right in here, but the top and the bottom are fins, the other is my base. So if I wanted to calculate the heat that was dumped into that one passage, what I would do is I'd say, well, I'm going to have kind of an overall efficiency thinking about finning, using the top and the bottom are fins, times some convection coefficient, they gave that to me, times some area, I can calculate that, times some T base minus T infinity. So they gave me these two temperatures, they gave me this one, a lot of work to get this, and I can get this with a little bit of work. What is that area? The area is going to be I go 8 millimeters, up 2 millimeters, 8 millimeters, down 2 millimeters. That's going to be my perimeter for that channel. That's going to be 8 plus 8, 16 plus 2 plus 2. That'll be 20 millimeters times, going back, 10 centimeters. And I'll turn that into meters squared. So I've got this area, right? Now it's just this overall efficiency. What do you think that overall efficiency is? If somebody said, you don't have time, you have to guess the overall efficiency, what are you going to guess? A little less than 100%. Because it's a pretty good conductor. It's made of aluminum. Even though the H is high, it's still not that high. And it's actually pretty thick. It's a 1 millimeter thick. This is kind of drawn to scale with the right proportion. So it's pretty thick right in here. The difference between the temperature at the base, which is 45, and the middle, this would be the lowest temperature anywhere, wouldn't it be? Is not going to be that much. It's going to be very low, the temperature difference. So I would even guess this to be 100%, and you'd have a pretty good answer. It'd actually be pretty close to the 3.73. But there's a lot of work to get that accuracy on that third significant figure. I know a lot of you like to get accuracy to 6 and 7 significant figures. So let's go. How are we going to get the improved accuracy?
So the area, did you take the area of the vent or the area of the fan?
This area is the area that is in contact between the solid and the fluid as it flows through the whole system. Because we want it for one passage. And the passage has this side, this top, that bottom. The white is the fluid passage, right? The air goes through this empty area. Okay, now to get a good estimate of eta naught, I have to use my equation. So eta naught is going to be 1 minus the area of the fin divided by the area total times 1 minus the efficiency of the fin. So let's worry about the area of the fin divided by area total. You could go back and do the same thing and think about, this really is a fin and a fin, and this is a base and a base, just looking at our passageway. And so for the total, it'll be our 20, that's denominator, numerator, denominator. That would be our 20 millimeters times our length, W, but it's going to cancel. And then the area of the, this is the area of the fin. Why does that look like a T? That's our fin area. That's going to be 8 times 8, 16. 16 millimeters times W. The W is canceled. The area ratio is 16 divided by 20. Is that 80%? So that's not that hard. I think we could handle calculating that area ratio, and it's 80%. Now the hard one. Yeah. Okay. So we're going to assume it's a constant rectangular cross-sectional fin out to the middle. Out the middle, it's like insulated. And so our formula for that fin efficiency is the hyperbolic tangent of ML divided by ML. Do I need L sub C? No, because it is actually insulated. It's symmetrical. All right, so L is going to be 4 millimeters, 0.004 meters. What is M? Well, we have to do a little work. That's the square root of the H P divided by K A so C. For our rectangular fin, P, our perimeter, is 2 W's plus 2 thicknesses. These are negligible. I mean, really, there's no heat transfer from the face, the butt end and of the faces. It's all the 2 W's. And then the cross-sectional area for conduction, that's going to be our thickness T times W. And so for our rectangular fin, you get the H divided by K, But the ratio of P divided by A sub C is 2 divided by T. It's even simpler. Just 2 divided by T. What was T? 1 millimeter. So we've given our H, we're given our K, we've given our T. It's a rectangular fin. We can calculate that M. This is probably one of the more frustrating parts. Guess what M is? M is going to be 35.41 over M. Let me clarify. M is equal to 35.4 inverse M. Do you see the potential confusion to students? 1M is the fin parameter. 1M is a meter unit. And I think they used this fin parameter when everything was in inches and foot, long before you tried to move over to SI. And then they said, well, let's stick with our fin parameter M, and we're going to move to SI, and our new unit of length is a meter. And so this always looks funny, this equation, when you have it like that. But there you go. So now you can multiply that by L, get the ML, do the efficiency. The efficiency of a single fin comes in very, very high. It comes in at 0.9933. So let me try and draw that. I don't know what my pen is doing today. Then when you calculate eta naught, it comes in at 99.5%. Huge, very high. Basically, if I was a designer, I'd say thin that out. You don't need it that thick. Save some aluminum. Okay? Open up the passage, or put more passages in that are not as far spaced. You don't need that thick of a fin. All right. So then you come back to this equation. You just calculate eta naught, and you can calculate Q. Did that help? So let me try and summarize. We handled this section 3.6. 3.7, we're not going to cover. Skip. Your favorite four-letter word for this class. Skip. Thermoelectric power. Skip. Micro, nano. Skip. Hey, we're done with this chapter. Yeah, next time we'll do a review, and we'll make sure that you're ready for the exam, which is 1 week from today. So I'm going to stop now. Thank you for your attention. Zach has a quiz.